first start with the concept of what is a force? What is a force? How would you describe it?
An action applied to a center mass that produces an acceleration.
Good. So something that produces an acceleration is the idea for a force. Okay, something that produces an acceleration. When won't it produce an acceleration? If that force is?
Countered.
Good. Balanced. Countered. Very good. So if I apply force to the desk right now and it's light enough, well, the locking mechanism in the wheels provide friction so the wheels can't turn. So it's the friction in the wheels that's preventing me from moving this. Now, it's clearly moving. I'm just probably screwing up bridge typing, sorry. But the idea would be that the force pushing back is enough. If I overcome that force, though, then the desk will start to move. So I'm giving it acceleration. And it may not be obvious because when you look at this, if I just do this lightly, it barely looks like I accelerated this. But acceleration is defined as change in velocity. So if its current velocity is 0, and you just get it to move even the smallest amount, you've given it acceleration, or you've accelerated the body. Now, in general, we talk about what is called the net force. What does net force mean? What does net force mean?
Total force is applied to an object, including the force you're pushing down on, and then the force countered.
That's an example, exactly. But the total force, I like that. Actually acting on an object. So the first thing we look at is this, when we say a force produces acceleration, right? F equals ma. But then we recognize that it's not a single force. It's the sum of all the forces that produce acceleration. The sum of all those forces. And some textbooks like to use the summation symbol, while others like to write F net. It's the same thing. Net or sum is the same concept here. So I could write it like that, or again, I could write it with the subscript of net for F net. Now, what else about forces do we know? We know this. If I push on this eraser at an angle, what am I really doing to it? I'm pushing at an angle. Yeah.
You're increasing force of friction, which decreases the net force of acted on the object.
This is totally right, Tristan, but way more detail than I even need. Simply though, much simpler than that. If I push at an angle, what am I actually doing is my question. So the idea is right what you're saying, but you're going way too far. If I push at an angle.
The force at an angle.
And therefore, if it's at an angle,
The force in x direction is decreasing.
more than that, if it's at an angle, specifically in physics, think about vectors.
And there's two, there's x and y.
There's x and y. There's x and y. The key to this chapter is to recognize that all the laws of vectors apply themselves. What you guys said were right answers, sorry. But I was looking for the concept of at an angle, you're getting components of it. So when we talk about forces, we want to also recognize that the sum of the forces applies to each direction. Okay, and in this course, we're really going to look at the x and the y direction. And you saw that last time. It also applies to the z direction, but we're going to be looking at only things that are moving in 2 dimensions, not 3 dimensions. Well, I should say that for now. There can come a time where we look at that. So fx equals max, fy equals may. So again, like projectile motion, I would highly recommend that you break your problem up into 2 directions. And in this chapter, we'll have a linking variable. We'll have several linking variables actually in this chapter. Okay, it won't just be time or v naught or theta naught. Remember that last chapter, the linking variables that were both in the y and the x direction for projectiles was the time it takes, the initial velocity, and the theta initially, the initial angle of launch. Those were the linking variables for projectile motion. For this topic, we don't have to jump into it yet, but does anyone remember from last year what the linking variable was here, or one of the main linking variables? Mass is on both sides, good. Right, mass is the same on both. What's another linking variable in the x and y? You have to recall the types of questions to answer this.
The angle.
Sure. Yeah, actually, good point. The angle, theta naught. Yeah.
T.
Tension is usually in both directions if we have something over a pulley.
I'm thinking time.
Oh, time. When we get to the kinematic portions of the problem, then time would also link it, but generally just for forces, just the types of forces.
Gravity.
No, gravity only acts in vertical. In inclined planes, we'll see how we can break gravity into components, but gravity only acts vertically.
Acceleration.
Acceleration, but they're different acceleration values. There's one other variable. You can't recall it. It's not the regular one that you think of. It's not something you can think of right off the bat. goes into your friction formula in the x direction. Not mu, you're on the right track. It goes into your friction formula in the x direction, while it's in another formula in the y direction. It's another variable, another type of force. We kind of make this force up.
Normal
Normal
force?
force, very good. Fn, remember normal force? Fn is the other linking variable. So normal force, if you recall, is like, hey, this book is here, right? Well, the book is at rest on the table. Why isn't it falling down? The table's pushing back up. We call that the normal force, the force that resists the direction of its motion. So normal force was that other linking variable. So we're going to get into all of these. So first, let's take a look at Newton's first law. Okay, Newton's first law simply tells us this. If there's no net force, there's no acceleration. There's no net force, there's no acceleration. So what does that imply? What does that imply? There are two cases from Newton's first law. Kristen?
Like, let's say you have like an object and you have force going one way and like an equal force going another way. If the net force is 0, then the object won't move.
Okay, so one scenario is an object at rest that is suddenly applied forces on both sides equal. It's not going to move. Agreed. That's one scenario.
If you like push against the wall?
Same thing, no, same scenario still, right? Still not moving. Give me the other scenario.
If something's already moving and there's no force applied to stop it, like friction or hitting something, then it won't stop.
What will it move at? At
A
what?
constant velocity.
Okay, so those are the two scenarios. If, again, Newton's first law says, if there's no net force, there's no acceleration. Acceleration is a change in velocity. So either it can have no velocity or a constant velocity. Again, if there's no net force, whenever this is true, we have one of two scenarios. Either it is at rest or it is at a constant velocity. It's one of those two always when the net force equals 0. And again, we're specifically talking about a single direction. So this book could be doing this, right? Look, it's got a net force in the x direction, right? But in the y direction, the entire time I'm doing this, the net force in the y direction is 0. It is not moving up or down. Not at all. Now, if I do this and launch it off the table, then gravity will do the net force acting down once it leaves the table. But while on the table, the normal force and gravity balance each other. What was the phrase for this in physics? When there's a balance, what do we say? What do we call it? Equilibrium. Okay, equilibrium. And it's important to recognize that equilibrium is not just in forces. Later on in this course, we're going to talk about rotational equilibrium, very similarly to what we're saying now. And that would be the sum of the torques. The sum of the torques equals 0 for that. Whereas here's the sum of the forces. Chris, you had a hand up. Londell, sorry, I didn't get to answer. A minute ago, you had a hand up. Okay, if you think of it, raise it again. Sorry, I was in the middle talking, I didn't answer you. So vectors are really important. We're going to use the same idea with vectors as we did last time. So let's draw an object real quick. There's my object. Let's draw a force acting. There's my force. Call that F. And let's call this angle theta. If I want the x component of that force, I use F cosine theta. If I want the y component of that force, I use F sine theta. Very similar to what we did with projectile motion. Now, notice where theta is. Theta is the angle between the applied force and the horizontal. The applied force and the horizontal. If you're given the other angle, its complement, you have to recognize that you have to take it away from 90 to figure out what theta is. Okay, so again, if given an angle like alpha, okay, in that diagram right there, alpha, you would have to be figuring out what theta is first. Or, if you know your math pretty well, what else could you do? Anyone know their math real well? What else could you do? You want to use alpha, and you don't want to use theta, you want to use alpha instead. What do you think, Max?
You can just switch the cosine with something.
Yeah. Remember, the cosine of 30 is the sine of 60, isn't it?
Yeah.
You remember that law from your pre-calc course? Okay, that was the idea about cofunctions. The secant of 20 equals the cosecant of 70. The tangent of 10 equals the cotangent of 80. It's always about complementary angles. So, theoretically, this is the answer. Or, you could write the following. Let's just, as Max said, you could say, instead of saying this, you could say this equals f sine of alpha, and this is f cosine of alpha. So if you want to, you could use this angle and then switch your sine to cosine. I personally have a tendency to look at the angle between the force and the horizontal and remember that cosine is x and sine is y. Check.
Are we gonna do bearings for angles and stuff, or is it just?
So you're going to be given like north, east, south, east, stuff like that?
Yeah.
Yeah, problems could give you a bearing. You could say that a force is applied at 40 degrees northeast. Well, you got to know that that means it's being pulled upward and to the right versus 40 degrees southeast, downward and to the right. Pulling down on it would increase the push down, which increases normal force, which increases friction, versus pulling up actually reduces the normal force. It kind of comes off the ground, and you have less friction. So the bearing does matter, absolutely. Yep. Throughout the whole course, you should be able to do that. So no matter what topic we're on, we should be able to recognize when an angle is given with a directional like northeast and southeast, what it means.
Would 40 degrees from northeast be from the x-axis or the y-axis?
X-axis. Whenever it says northeast, it means north of east. So we could say that this is 40 degrees northeast, or this is 50 degrees east of north. That's the weird one. Most people don't know that one. So let's take a look at what I'm saying here, okay? So this is east. Take a look at the pen, please. That's east. This is 40 degrees north of that. North of east. So put the word of there. Then when I go here, I can say, well, this is north. And this is 50 degrees east of north. This is north, now I'm going east of that. So if I get my directional from the horizontal, I'll say northeast, or northwest, or southeast, or southwest. What you're used to saying. It's very rare, unless you have done some sailing in your life, that you use bearings like east of north or west of north. It's not common to use that in colloquial language, I guess is the right word. Hey, but the idea is north of east is more useful, south of east is more useful. This works, but it's not traditionally written that way. But if a problem is given that way, you should understand that east of north physically means go north and then go east of that, and that's the angle that the problem is talking about. All right, I'm trying to not reiterate everything because obviously you guys covered this last year, but I want to also recognize that we do have to talk about important things. Okay, we are going to specifically focus in this course on what are called inertial reference frames. It's really not, and I was talking to Mr. Domish about this earlier today because I wanted to see how much of a focus the test has. And he said it's really not a huge focus on this test at all. When you're in college and you're studying engineering, you get to a course called dynamics. In dynamics, we talk about what are called non-inertial reference frames. For example, if I'm standing still on the Earth that is not accelerating, even though we know it is rotating, we kind of assume it's not, but it is. On the ground is my reference frame right now. The ground is not moving. It's a non-inertial reference frame. It's an inertial reference frame. And the idea behind it is that if the thing that you're on is either stationary or moving at a constant velocity, like you know those the walking conveyor belts in the airport, they move at a constant velocity. That is still considered an inertial reference frame. It's when you're standing on something or the object that you're interpreting is on something that is accelerating. So for example, if you had like a baseball on the back seat of a car, and the car is moving at a constant velocity, well then we can say it's an inertial reference frame. But the minute the car is accelerating, now the ball is in a reference frame that itself is accelerating. We're not going to get to problems in this course, so keep that in the back of your mind, that the problems are really going to focus on objects that are either stationary or moving on a body, or that body is moving on has a constant velocity. But it's not going to be, God bless you, it's not going to be moving on a desk that is itself accelerating. The object can be accelerating, but the surface that it's on will not be accelerating. It will not be accelerating. All right. Generally speaking, in physics, something you should know, not something that's super important, but something you should know, the idea, is that Newton's laws are actually, like Newtonian mechanics and the whole idea of inertial reference frames, are really important, but for only a select type of motion. If you approach the speed of light, you can't use Newtonian mechanics anymore. You have to use, anyone know what that's called?
Quantum?
No, that's the other one. Quantum is for like subatomic stuff you do, yeah, and that's true also, but we're going to get to that in a second. That's the second case I was going to talk about. What do you use when you get close to the speed of light? What did Einstein come up with? The theory of relativity. Okay? So laws of relativity hold true when you get closer to the speed of light. When you get to subatomic particles, you use quantum mechanics. But we're going to use what's called Newtonian mechanics. So all of our problems in this course, in this AP course in general, are going to be involving Newtonian mechanics. Okay? Keep that in the back of your mind so you know that. Mass. What is mass? What is mass? Give me an idea.
It's like the intrinsic property. It's like it's an intrinsic property of an object, so it's unchangeable no
Okay.
matter what place you go to.
I like that. It's an intrinsic property. It's technically what if you cut it in half and it's changeable.
Right.
Density is not changeable if you cut it in half, though.
That's true. And
So that's
density
a
is part of weight.
empirical value for
Part
that.
of density is part of mass.
Very good. And mass over volume, which is because you're changing both by cutting in half. Give me more about mass.
Just like the amount of matter in a space.
The amount of matter that makes up an object. That's like the traditional definition you've heard, right? Physical science, your older science courses. Give me more. Amount of matter. Measurement amount of matter. Okay. Anything else? I mentioned something different in my class last year. That's why I'm asking. I'm trying to see if you remember this one. Could also be considered a measurement of the inertia of an object. Mass could also be considered the measurement of inertia. Let's discuss why that is. This is where I can see like a multiple choice coming into play on the test. So measurement of inertia. What is inertia? Inertia is Newton's first law. And earlier, Matt, was it you that said it earlier, or somebody said it? Who gave me the answer earlier for Newton's first law? You said there are two types of motion. Either it can be moving at a constant velocity or it is stationary, right? An object in motion either stays in motion or stays at rest. Inertia is exactly that. So how do we think about mass as a measurement of inertia? Well, a simple example, and I could give this example last year, so if those want to remember this. You're at the driving range, right? You're hitting golf balls. One after the other, you're hitting golf balls. And then for some reason, a bowling ball appears. And you go to try and hit the bowling ball. Is it going to move like the golf ball moved? Definitely not, right? We all know that. The club will probably break, but it was not going to move like that.
Yeah.
The bowling ball has more desire to stay at rest than the golf ball does. And think about that logically. Try to push this building over. Is it going to move? Of course not. I mean, we are not going to be able to move it, I should say. Okay, but a storm that's crazy enough could move a building, could cause it to sway. The mass of the building is its measurement of inertia. It's its desire to stay at rest. So if you tried to push over your dad when you're like 2 years old, or your older brother when you're like a year old, does it work? It doesn't work very well. And you know that if you have younger siblings or younger cousins, they try to like push you in the leg, right? You know, when they're like this tall still, they'll like run into you and they're like, you're not moving, and they like push you and hit you and stuff, and you don't move. Because your measurement of inertia is so great compared to the force they can apply. Now, there's obviously also friction and stuff, right? We talk about that. If there was no friction, the littlest push would cause you to move. Because again, the littlest push is a force. That force creates acceleration. It's because friction is combating that force that it doesn't actually move. So if I'm standing here and my cousin or my niece just pushed me, I would move if there were no friction. But friction is what's allowing me to stay still. My inertia is what causes me not to move as quickly, though. So if I were to push this eraser like that, and then do the same thing to this book, look at the difference, right? Much less mass, so it accelerates much greater. Much more mass, barely accelerates. So again, the concept of mass is really it's just a ratio. It's a ratio of force to acceleration. The amount of force you apply and how much acceleration you get out. The more that is, the more value your mass is. Mass.
So is friction the only way stuff slows down?
That's a good question. No, unbalanced force could also cause it. So like an object is sliding and I just push it. But now me pushing it is really friction holding me there. So inherently friction is always doing the work to cause a loss in energy.
So is a vacuum something without any friction?
Depends on what type of friction you're talking about. Air resistance, yes. A vacuum just removes the gas out of the air. That's all it does. But if you're in a vacuum and you still rub your hand against something, there's still friction. There's absolutely still friction. There are no frictionless surfaces. Even things like Teflon or ice skate on ice, there still is some friction. Even like, what are those called? Levitating, magnetic levitation, maglev trains, even those involve friction. There is still friction between the film of air that is between the object and the surface that's magnetic. There's a little bit of friction there, but it's very close to being frictionless. Skiing is probably the closest thing to being frictionless that you could ever do. Ice skating is close, skiing is better. Because when you ski, there's a small layer of gas trapped between the actual skis and the snow that's giving you a little bit of lift. It's exactly like maglev trains were modeled off of skiing. They literally took skis. Skis have been around for hundreds of years. People used to cross, continents on skis. Came across the Bering Strait? No, what's the strait that connected? Was it Bering? Russia to Alaska? On literally skis. And people would cross-country ski to get across because very, very low friction. So very little energy allows you to keep moving when you're on skis. Well, the idea of skis have been around forever, and maglev trains modeled off of skis. That's literally where it came from, yeah.
Why does friction exist?
Friction exists because of interaction between two bodies. So, for example, this might seem smooth to you, and my hand might seem smooth, but there are ridges. The ridges here are interacting with the ridges here. That's kinetic friction I'm talking about. Static friction has to do with so there's surface charges and intermolecular bonds between the objects. So when your hand is still and you start to move it, I don't know if you recall this from last year, static friction is always harder to overcome than kinetic. Does anybody, you guys remember that? Okay. Like to push an object, it takes a lot, but once you get it going, it's not as bad to keep it moving, right? Because you're also overcoming those bonds. I think they're cohesive bonds. Cohesion is two separate materials, and adhesion is the same material. I forget which is which in chemistry. It's adhesion or cohesion between the two materials that's causing them to literally stick to each other. And then once you overcome that stickiness, in a sense, not the right word, right? But once you overcome that, then it smoothly moves over the surface. But there are two different types of friction, really. It's those ridges that are causing kinetic friction more. And remember, without friction, we would never have energy loss. Existence wouldn't make sense. Think about it. Existence is all about balance of energy. So if you have energy gain always and no energy loss, the universe would constantly be gaining energy. You have to have conservation of energy. That's one of your laws we're going to go over in 2 chapters now. So I'm getting ahead of myself, I guess. But the concept of conservation of energy proves to me that friction must exist. It must. Or else I could give mechanical input and it would go on forever and ever and ever. Next.
Is there ever a case where kinetic friction is stronger than static?
No. I say no, but maybe there's something I don't know about. But every physics book always says if for static friction that F is less than or equal to mu Fn for static because there's a limiting factor, and that F kinetic is always mu times Fn, but that F static is greater than or equal to F kinetic. There might be a situation that I'm not sure of, or it's something I don't know about. So maybe research that actually real quick while we're looking. Yeah.
Wait, kind of like back to the math. So like if a vacuum is the absence of the gas,
Correct.
then what's there?
Nothing. So gas is particles in the air. So around you right now, there are nitrogen, argon, oxygen, all these molecules that you're breathing in, right? Carbon dioxide coming out of your lungs. But if you removed everything out of the air, you physically wouldn't be able to breathe. There's nothing to breathe in. So the things in the air are what are causing that resistance you feel when you do this. So if there was nothing in the air, you would feel no resistance and thus no drag force. So in outer space, the idea is like, if you were to literally take a wrench and go like this in outer space, it will go end over end forever until it gets into the gravitational pull of some other bigger object and get pulled into that surface. But in outer space, that's the best example of no friction. Because if you throw an object, it's not touching another surface. Now, if that wrench was doing this, right, and then you know what space dust is, area of space dust? It's all the crap that's left over from all the stuff we sent to space. So there's a wrench, right, doing this, and then maybe there's a satellite. When it hits the satellite, it's going to cause an unbalanced force, and it's going to stop, or it's going to get rebounded, depending on the type of collision it is. But the idea is that if it didn't interact with any other body, it would just go on forever, because there's no air resistance or drag.
So just like nothing exists at all.
Correct. Vacuum is an absence of a gas in that container, system, closed volume, whatever you want to, it's many interpretations of that word, but the idea is the same as, remember, I think, did I show you guys, with you guys, about a bowling ball on a feather? Did we look at that here? Was that last year? It might have been last year, I don't know. But you just Google it. Google bowling ball feather vacuum someday, and you'll literally see a vacuum, a bowling ball and a feather fall at the exact same rate, which will blow your mind because you're used to seeing a feather do this. But it literally falls at the exact same rate when they suck all the air out of the chamber. It's a vacuum chamber is what it is. Max?
What's the gas with the lowest friction?
The gas with what?
Like the lowest friction.
I don't know, to be honest, Max. I'm not sure. I'm sure there's some chemical property that somehow affects the friction level of any fluid or gas. Because remember, a fluid is a liquid or a gas. So it's really fluid mechanics that studies the concept of some sort of resistive flow or viscous force to motion. So it can be a liquid or a gas, but they have different levels of friction. Temperature affects it, pressure affects it. There are a lot of parameters that go into it. So to simplify that into one thing, it's probably not one just simple answer to it. Okay, let's see. Oh, so the last piece I was mentioning here, though, we were on mass when we started talking about this, was the following. That mass could also, we said a measurement of inertia, but mass could also be thought of as the ratio of the force to the acceleration. And you're just solving Newton's law, right? Solve Newton's law, divide by A, you get F over A. I'm going to try to do a couple labs with you guys in this chapter, but I like to start when we get to friction more than we're here. So right now we could do a lab today, but it's really simple. Here's what we would literally do. We would take one of those carts and put it here. We would take a force sensor, and we would push the force sensor on the cart. Literally push it with the force sensor. The force sensor would measure the force. We would have a detector here and measure acceleration. And what we would notice is that if we double the force, it doubles the acceleration. If we triple the force, it triples the acceleration. It's a very simple lab. It's not worthy of an AP course at all. So I'm just giving you the demonstration of what it would be. And that concept is because it is mass that is the relationship. Remember when you look at formulas, the coefficient in the front we used to call the constant of proportionality? Do you remember with direct and indirect variation from math class? F equals, or Y equals KX, and Y equals K over X? That was directly proportional or indirectly proportional. Here we're going to see that M is the constant of proportionality. The more force you have, the more acceleration you get, and M is the variable that corresponds or relates those two values to each other. So this is another nice way to think about mass, okay? The net force over the resulting acceleration would give you the mass of an object. And because the mass of this book is not changing, Tristan told us that, or no, Chip told us that, sorry. The mass of this book isn't changing. Doesn't matter if I bring it here, to the moon, to Jupiter, the mass isn't changing. So, if I push and I get the acceleration, well, this number over this number gives me that mass. So if I double the force, the only way, if I double this, to keep this constant, would be to double acceleration. So I can do this, right? I can put a 2 here and a 2 here. They cancel, and I still get the mass out. So the ratio of force to acceleration is a good way to think about mass. All right. Now, in this course, it's also good to recognize, because now we're about calculus, that we can write this law as F equals M times, instead of A, what can I write? Instead of acceleration, calculus, what can I write instead of acceleration?
The integral of V.
Not the integral. Derivative, good. dv dt. Okay, this is the derivative of velocity, right? The derivative of velocity is acceleration. Another way to write that is m times v prime of t. Which notation are you used to right now? Do you use dy dx? Have you used y prime, f prime of x? Are these all somewhat familiar? So this is like the f prime of x notation. This is like the dy dx notation. Yeah.
Is this where like the calculus comes in with these
Yep.
problems, like just derivatives and things to find?
Well, eventually what we're going to do is we're going to get to the topic of an air resistance. And air resistance, it turns out, is a function of your velocity, when your velocity can change. So we're going to get into derivatives, and we're going to get into what are called integrals, which you guys are not there yet. Are you at antiderivatives yet?
Not quite. I think
So,
for the chapter.
soon you will be.
It's the next chapter.
Yeah, it's going to be coming up soon.
Round 3 is 4.
Perfect. So yeah, when we get to that idea, we'll have hopefully that under our tool belt, and we'll use integration for that part. And this is called separable integration. And I'm not going to get into too much of it now because it doesn't make sense to do it yet. What's another way of writing it then? Instead of dv dt.
d squared x over dt squared.
Well done. I like it. And you had it properly stated too. Very good. d squared x over dt squared. Again, it's stupid, but look at the squares. They look like they're in different spots. They are. It's not a mistake. This means the second derivative of x with respect to time in its second phase, meaning divided by time twice. Also written as x double prime of t. Okay? So yes, these equations can also be used for our law, for Newton's second law. When we get to momentum, we'll see how momentum is related to this. Do you remember what momentum's formula was from last year? P equals? What is it? mv. So it's P equals mv. Well, we can look here and see that P equals mv kind of plays a role because we're looking at m times another type of motion or one of our derivatives. So we'll see how the momentum and force are related by a derivative later on. Okay, but this is the idea of the first and second derivative for Newton's law. All right, I think that's what I want to go over in general, and now I want to jump into problems. Let me see if there's anything else. I'm going to get into free body diagrams in our first problem, so I'll talk about those. Okay, one last thing I should mention then. Yeah, right before this last problem. Okay, so, and by the way, I'm on page, just so you know, this is page 99 at the very end I'm talking about. I'm going to get into some problems in a minute on page 100. So, this last idea I want you to recognize is the following. When we talk about the sum of the forces acting on an object, we are not talking about any internal forces, because they're external forces that are acting on the object. So, for example, when I push on this book, the push that I'm applying is an external force. There are absolutely forces inside this book right now that are balancing each other. Like when I press this, it deforms the book a little bit. Literally, it does. When I walk across the room, I'm not very heavy, but I'm heavy enough. I actually am deforming the floor. Every time you sit in that chair, you're deforming your chair. There are internal stresses and forces that are keeping your chair as a solid. If there weren't internal forces in that chair, you would snap through the chair. You would literally break the chair. You would break the floor. It's the same concept. So there are definitely internal forces acting inside of a body, inside of an object. We are not going to concern ourselves with those. That's more of a materials engineering type of course you take in college. This is more of a macro scale. We're looking at things that are affecting the body externally. Okay? So the net force is the sum of all the external forces acting on the body. The net force is the sum of all the external forces, which is why we talk about a free body diagram as all the forces acting on the object, not by the object, on the object. Okay, so let's get into an example so we can start to see these. So I'm going to work off of example on page 100, okay? If any of you want to reference that later so you know where I'm working off of. So the problem says the following. There's a puck, okay? There's a puck here. And it's, actually, let me just do this. I did it last time, make it easier. Just going to do it quickly this time instead. Okay. All right, so here's the problem we're going to start with. So we have an example of using Newton's. Oh, wow. How does that look like that on your screen? On mine, it doesn't look a thing like that.
It's actually it's different resolution.
But where are these extra lines coming from?
It's actually crazy. It's not move the.
It's You're saying move it on the page?
Yeah.
What the heck is going on? Okay, so there we go. That works for now? Yeah, that was really weird. It looked like diffraction grading. Anyone know what diffraction grading is? Like when, yes, that's exactly it. Have ever seen like those images in electricity and magnetism when a light goes through a slit, so the double slit experiment, where the lights interact?
Yeah.
Double slit? Okay. I think that's what that was. It was like a diffraction. It looked like a diffraction gradient. Anyway.
Well, it's because of pixels.
Take your word on that. Alright, so here's some examples of how to use Newton's second law for a puck when one or two forces act on it. Parts A, B, and C of the figure, we'll look at the figure in a minute, show 3 situations where one or two forces act on a puck that moves on a frictionless ice along an x-axis in one dimension. A lot of words there. Now, for general problems, if friction is not stated, the assumption is the surface is frictionless. So on the AP exam, if you're not given anything about friction, or if you're not told anything about friction, the assumption you make is that it's frictionless. Now, if the problem, though, involves work kinetic energy theorem, and the energy before it moves is, say, 20 joules, and the energy at the end is 17 joules, there must have been friction there, and that's the loss of joules or loss of energy. So we'll get to that with conservation of energy, but I want you to recognize with a lot of problems, the statement about friction will be made. You'll be given a coefficient of friction, or you'll be asked to determine the coefficient of kinetic or static friction. Here it is frictionless. The puck's mass is given, the forces F1 and F2 are given, 4 newtons and 2 newtons. F3 is directed at an angle of 30 degrees, and its value is 1 newton. In each situation, determine the acceleration. Let me give you a quick diagram so you can see what I'm referring to. So here's the first diagram. So in figure 1, we've got only a force acting on a puck. Okay, that's the entire diagram for figure number 1. The problem says, determine the acceleration on or of the object. To determine the acceleration of the object. So I start by drawing a free body diagram. Every single problem can be drawn with a free body diagram. You're going to see that this year. When we get to forces, with forces, obviously. When you get to forces in this topic, you always draw free body diagrams. Without the free body diagram, your governing equation does not really hold true. Newton's second law is our governing equation, F equals ma. But the free body diagram is so important. Every problem on the AP exam, those part 2s, the longer ones, when they involve forces, are going to either tell you to draw a free body diagram, or you're just going to do it. And you'll get points for your free body diagram. It's like free points if you just draw the free body diagram. That's how important it is that they're willing to give you points for doing that. So for this problem, I would start, and I always start with my object as a dot. Okay, for free body diagrams, it is useful to draw a point in space. Later in the course, when we get to rotation, it's going to matter where I push on this, right? Look, I push on one side versus the other, it rotates differently. I push in the middle, it moves smoothly. The assumption in this chapter is that you're always pushing at the center of mass. So instead of drawing the full object, the puck, I take all of that mass and I concentrate it down into a point. And I call that the center of mass. And we'll get into center of mass a little bit later, but for now, this is my free body diagram. What is my external force? What is my external force? And again, gravity is not existent right now. Nothing about gravity is given. I would give you a scenario, I'll tell you it's on a tabletop. This is just a puck moving. We don't know anything else about it. We don't know if there's gravitational force. Maybe it's in space that this is happening. So my free body diagram would literally only have one force. Okay, that's F1 right there. So my diagram and my free body diagram are pretty much the same here, right? They're really not much different. And that's going to change, obviously. This is only a very simple example, which is why this is true. I then say to myself, okay, this is moving left to right, so the sum of the forces in the x direction equals max. I know that F1 is acting in the positive direction, so when I add up my forces, I've got F1 plus nothing else. I'm going to put 0 for a minute because there's no other forces. I'm never going to put 0 after this. Okay, I'm just putting it there to say that there are no other forces, and that equals ma. And a is in the x direction. So the mass was given as 0.2 kilograms. The unbalanced force that's applied is 4 newtons. 4 newtons divided by 0.2 kilograms will give me 20 meters per second squared.
So the net force is on the left.
So the net force is always what replaces F net, which in this case, yes, is right here, which is this entire thing right here. Now again, Tristan, I would never put plus 0, okay? I'm just putting it there today. Because if there was another force acting, I'd have to put that value, and another force, and another. You could have 1,000 forces as long as you add them all together on the one side of the equation and set it equal to ma. Set it equal to ma. So, let's go ahead and go through this again. To solve this equation, we simply divide both sides by m, and we get the acceleration. Again, 4 newtons over 0.2 kilos equals 20 meters per second squared. Now, because of the fact that you guys took physics already, I didn't go into units. What is a newton? What is a newton comprised of? Okay, I see one hand. Should be instantaneous. So let's go over this. So I don't even care about the answer. We'll talk real quick. Here's what's important. Use your equation to help you with units. Look at the governing equation. It's right here, isn't it? And what are the units of this? Right here. What are its units? What are the units of mass? Acceleration. So kilogram times meter per second squared is a? That's what a newton is. You see what I'm saying? If you ever forget what your units are, think about the equation. This side says newtons. Newtons have to be equal to whatever these units are, which are kilogram times meters per second squared. So if you're forgetting what a newton is, you take newtons and divide by kilograms, you're just taking whatever this was and dividing by this, leaving you with this, which is meters per second squared. So if you didn't know that, if you didn't know what the unit of a newton was, write it at the top, up here. 1 newton is equal to 1 kilogram times 1, I'm running out of room, sorry, on my screen, times 1 meter per second squared. Okay, that's what a newton really is. It's a kilogram times a meter per second squared. So how else would I describe what a newton is? It's the amount of force needed, fill in the blank.
Accelerate the
Use numbers. The amount of force needed to accelerate at a rate of? Very good. That's what a newton is. It's literally what you would need to make something that's a kilogram move at an accelerated rate of 1 meter per second squared. That's by definition what it is. Kilograms times meters per second squared. Yep. Yep. You can write it as one giant unit, kgm over s squared, and that's fine. Or I would write it just simply as a newton itself. So that's the easy example, right? That's the first part of this. Let's go to the second part of this problem. Same problem still. We're going to get a little wacky. Oh, it's still good, actually. We're still okay. It's weird, right? It's a certain, yeah, look at that. Look at that. That's crazy. All right, whatever. I'm getting too excited. So the second scenario, so this is scenario number 1. Scenario number 2 was the following. And this is right out of your text. Scenario number 2 said, now you've got the puck here, F1 pulling to the right, and F2 pulling back. That's scenario number 2. So we right away, we take a look, we draw a free body diagram. We've got the free body diagram here. There's F1, there's F2. Just put a little line here so we can keep working in this area. We then take a look at Newton's second law, and we say that the sum of the forces in the x direction equals max, and the forces acting in the x direction are twofold. We have F1 and we have F2. What do I do when I put them in here, though? How do I write it? Do I write F1 plus F2? Chip, you're saying no. Chip's shaking his head no. Why don't I write F1 plus F2? Why wouldn't that be appropriate for this problem? Because I just said sum, and to me sum means to add, right? Sum of forces. Add the forces. Kara, what do you think?
Opposing forces.
They're opposing forces. So how should I write it, Kara?
So you should do F1 minus F2.
And if I wanted to make it a sum, how could I write that?
You just do F1 plus negative.
Very good. And this is the way we should start deriving in our mind. But yes, Kara's totally right. I would personally write it like this. Okay, plus a negative is what subtraction is defined as. So I would agree with Kara and write F1 minus F2. But in your mind, you need to start thinking about it this way. Vectors, 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 right? Force is a vector. It has a direction. That direction definitely matters. And as a result, we can go ahead and solve for A. Divide by M. Oh, now it's getting wacky. Sorry. We're going to lose the image soon. Oh, no, it comes back, actually. I can't figure it out, which is weird. There we go. That's better. Kind of. So divide by M, and there's the acceleration. F1 is given as 4, F2 is given as 2, all over 0.2, which will yield an answer for acceleration of 10 meters per second squared. Yeah, sure.
If the force is directed in the opposite direction of like another force, could you also do like cosine 180?
Cosine 180 is -1, so therefore you could. You could say F1 plus F2 cos 180 equals MA. So instead of putting a negative here, you could put cos 180, and then the cos 180 becomes -1 inherently. Yep. Really, really good idea. And we're going to see that more with the work kinetic energy theorem. We're going to use that idea. Situation number 3. The puck is now here. The puck still has F2 pulling against it, but it now has F3, and F3 is pulling down at an angle of, I don't know what the number turned out to be, what they gave, 30 degrees, yeah. 30 degrees south of east. So here's my third diagram now. We're slowly working our way up into vector components. So my third diagram is given there. And again, the question we're trying to figure out is in each scenario, what is the acceleration of the puck? What is the acceleration of the puck? So, in this third scenario here, what do I do with F3? What's the first thing I do?
Did F1 exist as well?
In this diagram, there was no F1 in the book. I'm just following their example. So F1 is not involved in part 3. So like the first one only had F1, this had F1 and F2, this only involves F2 and F3. It's just 3 different scenarios. It doesn't matter what they, I mean, I could add F1 and it would still just be a different problem. It's the same thing. And what do I do with that force F3?
Split it into its X and Y component.
Yeah, always components. So my free body diagram, I like to draw it with components, but I'm just telling you now, you have to choose one or the other. You can't draw the original force and then add components to it. So it's either one or the other. So what I mean is this. My free body diagram could be this. Okay? And instead of 30, I should start using symbols, right? Theta. I should call these symbols theta instead of 30. Because if 30 changes, then we're just going to call those theta. I'm going to call it theta for now as an angle. So I could draw my free body diagram like that. I'd like to draw my free body diagram again afterward. So I would start with the original setup. And then I would redraw it. Here's what I would do. I would again draw my object at the center. Pull back with F2. Then how would I draw F3? How would I draw F3? Go ahead, Em.
Well, you put one arrow going to the right in the x direction and do F3 cosine theta. And then one going down, F3 sine theta.
Very good. Okay, so that's another way to simplify your free body diagram. And you're going to notice that throughout this course that it's really much easier if everything is in one or the other direction. When it's at an angle and you try to analyze it, it's not as obvious how your equations hold. So, for this example, here's my first question for you. My first question. Vertically, what would be the acceleration? Vertically, how would you figure it out? What would you do? Okay.
It would be F3 sine theta divided by F equals AY.
You're missing one thing. It's acting.
Downward direction.
Yeah. So that would be my governing equation for the y direction. Okay, that would be the y direction. Because there's only one force acting in the y direction, and it's acting down, so I put a negative symbol. And then yes, as Spence said, let's divide by m to get the acceleration in the y direction. And the answer is negative because it's going to accelerate downward. Now, that's only the y direction. We also have to consider the x direction. In the x direction, what else do we have for the x direction? Okay, so that was the y direction for this problem. And now let's look at the x direction for the same problem. Sorry, it's the same problem, so I shouldn't really put a line here. Pat, what do you think for the x direction? What forces are acting left and right here? Left and right. What are you seeing in the free body diagram?
F3 cosine theta and F2.
Okay. And how would I write it as an equation then? One is pulling right, one is pulling left, so what do I write?
F3
Very good. Equals MA. Yes. Very good. Okay? So that's my equation in the x direction. And then want to solve for acceleration. I go ahead and divide by mass. Okay? I don't know what those numbers are going to be, and that's not actually as important right now. Okay? But the idea I want you to see is that you're looking at the y direction and the x direction independently of each other. Questions at all on this idea, on this problem, on anything we've gone over so far, on how to keep Chip wide awake in that corner over there because he looks like he might fall asleep soon? I can't tell. I'm kidding. It's fine. Relax for a little. This is an intro to this section, so I'm hoping this is review to people right now. So if you're like, oh, this is easy, this is boring, it should be right now. It should be a little bit of review right now. Okay, so what I want to do next is take a look at a second example. Yeah, this one's a really good one. Okay, so let's look at page 101. This is page 101 and let me just quickly take an image of this again. Page 101. Yeah, if you guys have the book in front of you, feel free to also do the same thing I'm doing here. So there's the question, and then I think we have an image. Yeah, it's a cookie tin, I know. And then here's the actual image itself it's giving. Hold on. Oops, my cursor was in the way. Okay. Sorry, they're kind of like at an angle, but that works, right? Okay. Yeah. Go back to previous slide. Hold on, record. Okay. In the overhead view we're seeing here, the cookie tin with a mass of 2 kilograms is accelerated at 3 meters per second in the direction shown by vector A. So it's at an angle, right? The acceleration is at an angle. Over a frictionless horizontal surface, so on a plane. The acceleration is caused by 3 horizontal forces, only 2 of which are shown. F1 is shown, and F2. There's F2 on the y-axis. It's kind of hard to see it. Okay, F2 is on the y-axis right there. So those 2 forces are given, and the question is, what is the third force that causes this acceleration? Okay, what is the third force that causes it? So let's start listing all of our info first. So remember with projectile motion, I said listing the givens is really important. That'll come up here as well. So I'm going to start with acceleration in general, not x or y. Acceleration in the problem is given, 3 meters per second squared. Okay, it's literally in the problem. I'm reading it out of there. The mass of the cookie tin is given, 2 kilos. The force applied, F1, is given, 10 newtons. The force applied, F2, is given, 20 newtons. Next, I got to start listing a bunch of thetas. The theta for the acceleration is 50 degrees. And then theta for force 1 is, now this is where it's going to get a little bit tricky, right? 30 degrees, what am I going to write here? Southwest. Okay, the first one I should have written as northeast. And notice where I'm putting my theta values. I'm literally listing them below their corresponding portion. How about F2? What would F2's theta value be, or how would I appropriate that in the problem?
That'd be 90 degrees.
It would be 90. Now, would I want to write 90, or what would I just think about instead? F2 is acting only upward, only in the y direction. So when something is only acting horizontally or only acting vertically, it doesn't make sense to use 0 or 90 degrees as the angle. Just in your mind, recognize that 0 degrees means go in the x direction. 90 degrees means go in the y direction. But I don't need to write that here. And I can see it in the diagram that's acting only vertically, F2. Okay so far? All right. So now we want to take a look and say to ourselves, where's F3, right? What's the force F3 is acting at? What's the angle that F3 is acting at? How can we figure out its components and the actual overall magnitude. So we need to look at our directionals separately again. Let's take a look at our free body diagram to help us first. I'm going to draw it in the top right. So here's our object. Here's F1. Here's F2. How do I draw F3? How do I draw F3?
It would be positive horizontally. But with like a question mark.
Okay. I'm with you halfway. Need more than that. What does F3 do? Remember, F3 is what's causing this to accelerate at the accelerated motion, right? Which way is the accelerated motion acting?
50 degrees northeast.
Yeah, northeast, right? So the third force and the first force together, the third force and the second force together are probably going to both pull upward to combat this. I said probably, but I don't know, right? Then what about the other part of this? It's going to definitely go to the right. Agree with that?
Yeah.
Everybody sees that, right? Look at the acceleration vector. This object is going to eventually move up and to the right. Since this pulls down and to the left, and this only pulls up, the third force has to pull to the right. We know that for a fact. But we don't know the angle it's at. We don't know its value. So for now, I might just want to say F3 equals, as Matt said, question mark, and then theta 3 equals question mark. What angles? And now theta 3 might be above the axis. It might be below the axis. Right? So the angle could be like that for F3. Or it could be like that for F3. Maybe F3 is literally pulling down and to the right instead. So maybe that's F3. But I can't draw all the options for F3 right now, right? So for this problem, I'm simply going to draw one of them, and then based on my answers, I'm going to adjust accordingly based on my answers. So now that we have this diagram drawn, we could start to look at our directionals. So I'm going to start with the x direction over here, and the y direction over here. In the x direction, talk to me. What is going on here? How do I write my equation? Oh man, right? What do I do? What do I do? What do I do? What do you think?
Maybe find all the components, maybe find all the x components first, and then from there you can find the x component of the F3.
Okay, I like that. Find all the x components, whatever's acting in the x direction. So tell me, what's acting in the x direction? What force?
Force 1 is acting with a force of 10 newtons, 30 degrees southwest.
And that's negative? I know it rang, guys. Give me one more second. Then to this, we're going to add on F3. Now, we don't know the angle theta yet. We can put cosine theta here, but we don't know it. So the easier way is just to leave F3 alone for now and call this F3x, the x component. Don't even put the angle theta in there, just put the x component and set that equal to m times a cosine 50. Why is a times cosine of 50? Why is the acceleration times cosine of 50 in this problem?
Because that's the angle it's at.
Acceleration is at an angle, which means the acceleration is to the right and it's upward. Okay? What I'd like you to do, guys, is the following. I'm going to see you again next week, so I don't want you to have the whole weekend to do nothing. I mean, it's not much, but I'd like